One of the first ways that the concept of integration tends to be introduced is in the context of areas under a curve. So I want to take a look at this now, and later on down the line, we'll come back and tie this concept of integration, area under a curve, back to the concepts that we related to antiderivatives in the previous section. So let me just call this integration, which is again something we haven't even defined yet, but integration as area under a curve. And I want to take a look at a particular area. So let me draw a picture here. Here's my x-axis, my y-axis. Here's some function, y equals f of x. And maybe we're interested in this region, which we'll call S, between x equals a and x equals b. So this shaded region here is what we're trying to find the area of. So we want the area below y equals f of x, above the x-axis, and between x equals a on the left and x equals b on the right. That's the area that we're looking for, the region that we're calling S. Later on down the line, so you'll notice right now our y equals f of x, that function is entirely above the x-axis. Later on we will relax this constraint and allow this graph, this curve, to even come down here below the x-axis. We'll talk about that later. Okay, so before we try to find this weird area under the curve, I want to talk about just finding areas in general. So how do we find other areas? How do we find other areas? So for example, if we're dealing with a rectangle, this is one I would expect you to more or less have memorized. So here's my rectangle. I'll call this the width, call this the length, and the area is equal to that length times the width. A triangle is another one I'd expect you to probably know off the top of your head. If this is my triangle, and if I have this height given, and that's a right angle right there, and this bottom has a length of b, the area of this is 1/2 base times height. And you can get this by basically chopping this triangle up into weird ways and turning it into a rectangle. So basically you can kind of break it up into various pieces. I'm not going to focus on that here. One other shape that might be useful is a trapezoid. And our trapezoid shape will look something like this. Okay, so there's our trapezoid shape. It is also going to have a height, that's a right angle, and it's going to have two bases, base 1 and base 2 being these two parallel sides. The area of this one requires us to take the average of those two bases, so b1 plus b2 over 2, and multiply that by the height. In all three cases, the area is the product of two lengths. Here, a vertical length, a horizontal length, a vertical length and a horizontal length, a vertical length, and a horizontal length that happens to be the average of these two other horizontal lengths. This makes sense. The units make sense. Area, square feet, square inches, square miles is going to involve a length scale times another length scale. A length squared. That's how we get units of area. So this is what we should expect to see going forward. If we have more complicated shapes, so if our shapes are more complicated, we can often cut them up into easier shapes. So all I mean by this is if I give you some weird shape, here's some weird, if this is the shape that I want to find the area of, we can cut this weird shape up into triangles, for example. I can cut that piece up from there to there. We can go from here to here, here to here, here to here. I can cut this up into a bunch of different triangles and call that one A1, that one A2, that one A3, and so on through all of the other ones, and I can just add them up. The total area is just going to be A1 plus A2 plus A3 plus however many sections we've cut this thing up into. So we can do that for these complicated shapes, but so far, all these shapes have been polygons. And so what I mean by that is they all have straight sides. Every single side of this shape was a straight line. That's not true of this shape S that we're trying to find here. One of its sides is curved. So how can we find the area when we've got a curved shape? So what if the sides are curved? So that's going to be our goal. We're going to try to figure out how to find the area of a shape that has curved sides. So I want to take a look at an example and think about how we're going to do this. So again, let me start with a shape here. Here's my X and Y coordinates. Here's my curve, goes something like this. And I don't know, maybe it's even a given function. Y equals x squared plus 1. Hey monkey, my son's coming to say hi. Arlo, I'm working right now. I love you too. I'll see you in a little bit. Sorry about that, guys. Okay, so maybe this occurs at a height of 1. That function is y equals x squared. And maybe this point right here, I haven't drawn that very accurate. Let's make it like right here-ish. That's slightly more accurate. It's right here-ish. Maybe this is the point 1, comma 2. When I plug in x equals 1 right here, I'd get 1 squared. That'd be 1. I'd add another 1 to that, and I would get 2. So this point would be on that curve. And maybe I'm interested in finding the area of this region from here to here underneath the curve. So there's the region that I want to find the area of. I can do that by starting to chop this up into little pieces the way that we did before. So maybe in this case I'm going to cut it up into 4 pieces. I can call this one S1, S2, S3, and S4, where these points are, again, x equals 0. This would be at the point 1/4. Here would be a half. Here would be 3/4. 3/4. I don't know why my pen is really not working now. Yes. 3/4. 3/4. 3/4. Okay. You get the idea. Let me try this again, see if I can figure out what's going on with my pen here. This point is 1. That's 0. So 1/4, 1/2, 3/4. Okay, so there's the point. Phew. Okay. Now I've got it cut up into shapes where 3 of the sides are straight lines, so the 2 sides left and right and the bottom are all straight lines, but the top is still curved. But it looks really close to being straight, right? It's almost a straight line. And so this is kind of the idea. We're going to approximate this shape, or the area of this shape, by cutting it up into sections and treating those sections as though they were some of these easy shapes from up here. So the first I'm going to do is just treat it like a rectangle. And we'll see that we have some approximations. So we want this area, that whole region S, and to find it, we're going to have some approximations. So we have several possible approximations. The first one, I'll kind of sketch them. Again, if we assume that this is the shape of that curve. The first one would be where we take this region, right there. I've got my 4 sections. And I use the right endpoint of each section to approximate these things with just little rectangles. So I'm using the right endpoints to pick out the height of the rectangle. So again, I'm using the right side of this box to pick out the function value of the actual curve there. Here's our y equals x squared plus 1. And I'm using the height at the right end of each interval to pick out what the height should be. So that's how we're deciding what the height should be. So we're using all the right endpoints for the heights. And clearly, comparing the area of all of these 4 rectangles to the area of the actual curve, I'm going to get an overestimate when I add up those 4 areas. So let me label everything here. There's x, there's y. This will give an overestimate of our area. I can tell that because, again, the rectangles, the area of the rectangles is clearly larger than the area of the curved region underneath, because these rectangles go above the curve. Another possibility. So let me give it another copy of this same drawing. So there's my x and my y. And here's my curve. Oops. Let's try this again. Good enough. Here's y equals x squared plus 1. And now I'm going to pick, instead of picking the right endpoints, so using, In this case, I used that point, that point, that point, and that point to pick the heights. In this one, I'm going to pick all the left endpoints. So I want to go to the same place here, and I want to chop this up the same way. But now instead of using all those endpoints on the right sides, I'm going to use all the left endpoints. So I'm going to use this one for the first rectangle, this one for the second, this one for the third, this one for the fourth. And that will give me a height that looks like that, 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 and that. Those are the rectangles that I would use to sum up, to approximate the height. So these are all of the left endpoints. See if I can actually write here, endpoints that I'm using to determine all of the heights. And it gives us an underestimate of the true area, because the heights of all of these rectangles are below the curve. Instead of using rectangles, I could approximate the heights using trapezoids. So from this point to this point, a straight line. From this point to this point, a straight line. From this point to this point, a straight line. From this point to this point, a straight line. So this one is going to be, we're using trapezoids. And we get even better results. So we get a closer approximation. If you think about it, going back to the formula for an area of a trapezoid, way back here, the formula for the area of a trapezoid is we take the average of the two bases, which are the two parallel sides, divide it by, so we add them up and divide by 2 to get their average, and multiply that by the height, which is the distance between those two parallel sides. And that gives us our area. Coming back down to here, that means that for these ones, these are the parallel sides. This would maybe be our B1, and this would be B2, and we would take the average of the two parallel sides. This distance in between would be what we called h before. So I would average these two, multiply by h, and that would give me the area. Effectively, it's the same as doing this shape. So let's do it in green. It's the same as if I were to take this shape, where this thing winds up being basically, you know, the average, this height, this distance that we're using here is B1 plus B2 divided by 2. So we could do it with rectangles like that. In this case, we're basically taking half the weight of all the left endpoints, half the weight of all the right endpoints. One other way we could do it is still with rectangles. X, Y, here's our shape. And for the heights of my rectangles, instead of using just the left or right endpoint, I could use this point, where this point is the midpoint. Do the same thing for this one. Use that height. Same thing here. Use that height. Same thing here. Use that height. This midpoint one, you can tell, will also be a better approximation than either, so it's also going to be a close approximation, closer than either of the first two that we did, because for each rectangle there's a portion of the rectangle that is above the curve, that's an overestimate, but there's also a portion of the rectangle that's below the curve and is an underestimate. So here's the above, here's the below for this one. Those look very close to the same amounts of area. Same thing here. There's the above, there's the below, above, below, above, below. There's some over approximation, there's some under approximation. We get a closer approximation than just doing a left or right-handed endpoints for our rectangles. So these are a lot of the different options. At the end of the day, our goal is going to be to utilize the idea of limits to take this from an approximation and make it exact. So let me just say, here's the formulas. So these yield the formulas that look like the following. So for that first one, if we're looking at the right endpoint example. So I'll go back up and look at that real quickly. My area is approximately the area of 4 rectangles added together. So let's go take a look at those rectangles. My right endpoints. Okay, so here's that example in red. The area of this first rectangle, I need to take the height of the function at its right endpoint. And if we look up at the picture that we had above, this right endpoint, that is x equals 1/4. This next right endpoint for the second rectangle would be 1/2. The third one will be at 3/4. The fourth one will be at 1. So basically I'm going to use these 4 points as my x coordinates to compute the heights that I'm going to use for my rectangles at, because those are all the right endpoints. So again, 1/4 was the first one, then at 1/2, right? So the first point is I will take f of 1/4, that's going to be the height. And I'm going to multiply it by what I'm going to call delta x, which is basically the width. Coming back up to our picture, I'm going to call this distance right there delta x. So in this case, it's equal to 1/4 as well. It's the distance, the width of all of the rectangles. So I've got f of 1/4 times delta x. That's the area of the first triangle. So this is the height, and this is the width. And that gives me the first rectangle. Then the next rectangle, the height is at the point 1/2. That's the right side of the second rectangle times delta x. Then we'll do f of 3/4. That's the height of the third rectangle, just the function evaluated at the point 3/4 times its delta x. And then the last one, f of 1. 1 is the right endpoint of that last rectangle times its delta x. If we actually plug these values in to the calculator, remember, f of x is equal to, in this case, x squared plus 1. That was the graph that we were using. And remember that delta x is 1/4. So if I just plug in 1/4 into my f of x, 1/4 squared is going to be 1/16 plus 1. So I'll get like 1 1/16 for this height. I'll multiply it by 1/4, and I would get some number here. I would do the same thing for this pair, and this pair, and I would sum them all up. And when you sum them all up, what I'm getting in this case is approximately 1.4687 is what I got doing that on a calculator. So again, just evaluate the function at these x coordinates. Those are the x coordinates of all the right endpoints. They will give you all the heights that we need to use for our rectangles. The widths are all going to be a quarter because we split that region up into 4 equal sections, and it was a region that started at x equals 0 and ended at x equals 1. So this is our approximation. This is the one that we said we thought, looking at the picture, was going to give us an overestimate. Right? That's the picture. Here's the 4 points that we used: 1/4, 1/2, 3/4, and 1. And we just found the height of the function at each of those points and used those for the heights of these 4 respective rectangles. The next one I'm going to do is the left end points. So now instead of using the point 1/4, 1/2, 3/4, and 1, I'm going to use the point 0, 1/4, 1/2, and 3/4, all the left endpoints of these 4 rectangles. And what we'll get if we use all of the left endpoints instead is going to be an area that's approximately equal to, so we're going to get f of 0, that's the left endpoint of the first one, times delta x, plus f of 1/4 times delta x, plus f of 1/2 times delta x, plus f of 3/4 times delta x. So this is using all of the left endpoints of each of those rectangles. And doing the same thing on the calculator, plugging these in, I wind up getting about 1.21875. So this was supposed to be an overestimate, and this, looking at that picture, we expect to be an underestimate. So we expect the true area to be somewhere between those two numbers. At the end of the day, so you'll have a few problems kind of like this on the homework, but at the end of the day, the question that's really important is how do we make our approximation better? So looking at our picture, way back up here at the top, we went through all the different shapes we could use. We saw that we used the right endpoints and use rectangles, the left endpoints and use rectangles. We could do the midpoints and do rectangles. We could do trapezoids instead of rectangles. All of them are going to be estimates. What would be better, regardless of which one of those I pick, is to get a better estimate. I want to use smaller pieces. I want to cut it up into more pieces that are smaller. Here's our shape. X, y equals x squared plus 1. Here's our shape. This approximation that we just did, let's, for the sake of argument, do left endpoints. So we're doing the underestimates of all of them. We just saw that that gives us an okay approximation, but what would be better? Well, if I just used more rectangles that were smaller, I would have a better approximation. So why not use, again, we're cutting it off here, instead of using 4 rectangles, let's use 8. And now here's all of my rectangles. Same shape, so here's n equals 4. We're letting n be the number of rectangles. Here's n equals 8 rectangles. I could go all the way up to 16 rectangles, and we're just going to get better and better and better. if we use more rectangles, and notice that by using more rectangles, what's happening to the width of each rectangle? This is our delta x. What is happening to delta x? So as we use more rectangles, meaning that we're making delta x smaller, our approximation gets better. So you'll do some, again, on the homework where you use 4 rectangles or something like that, but the long-term goal is to say, what if we use an infinite number of rectangles? Instead of just using a finite number, if I let this width go to 0, and I let the number of rectangles that we use go to infinity, so if I take this interval and I chop it up into an infinite number of pieces, our approximation will become exact. So we eventually want to use an infinite number of rectangles, each with a delta x of essentially 0, 0-ish, we'll say. Right? That's kind of the idea. The more that we use, the smaller delta x becomes, and we're going to be looking at, just like we've done in calculus all semester, looking at this balance of an infinite number of things, each of whom individually will have an area of 0. So we're going to add up an infinite number of zeros and somehow get this finite result in between. Okay, so how can we do this carefully? So let's do this. Let's do this carefully. I'm going to label the point where we evaluate f of x. For each rectangle. So to get the height of each rectangle. I'm going to label those points x sub I. And so it doesn't matter whether I'm using the left point, the right point, the midpoint, any other point in between. If we use a bunch of rectangles, so I'm going to let I vary from 1 for the first rectangle, 2 for the second, all the way up to, let's say we've got n total rectangles. And eventually we're going to take the limit as n goes to infinity, essentially. So our area, following the formula that we had before, is essentially this. I need to take the first height, so f evaluated at x1, and multiply that by delta x. Then I need to add to that f evaluated at x2, multiply that by its delta x, plus so on and so forth, all the way to the last one, f of xn, where again, that's our nth rectangle that we're evaluating, times the delta x. And again, because we're using n total rectangles, in this case, that delta x would be equal to b minus a, where again, b and a represent the 2 endpoints of the region that we're trying to compute the area. And we're just dividing that up into n equal pieces. So going back up to our picture from the very, very beginning, way back here, here's what a and b are. A and b are just the endpoints of the region that we're going to be computing the area of. A is our starting point, b is our ending point, and we're just chopping that region up into n pieces. So the width of each one of those pieces, our delta x, is just going to be whatever b minus a is, which is this distance, chopped up into n total pieces. So that's why we do b minus a and then divide it by n. Okay, so let's go back down to our picture here. B minus a over n. Okay, so I want to write out our formula. One thing I need to make sure I made clear, this is not an exact, we're still approximating, so this is approximately true. Right, we're using n rectangles to come up with our approximation. If we use summation notation, because that's all we're doing here is summing up a bunch of things, and we use our index notation here, I can rewrite this as the sum from I equals 1 up to n of f of xi times delta x, where again delta x is equal to b minus a over n. So this is called summation notation. This thing here, if you haven't seen it before, this is summation notation. Essentially, this symbol, which is the Greek letter sigma, a little spiky backwards 3 thing, so it's the capital letter sigma, it just means add up. Or sum. That's why it's called summation notation. We're just summing all of these things. And this bottom number down here, I equals 1, tells us where we're going to start summing, and this number up at the top tells us where we're going to start. So we're going to sum from 1 up to n, f of xi, so starting with 1 here, then 2, then 3, all the way up to n, just like we saw here, 1, then 2, all the way up to n, of f evaluated at each of those points times the associated delta x, with again delta x being defined the same way that we did before. So this is a shorthand way of writing what we've written here in sort of long form. Again, this is an approximation. To make this approximation exact, all we need to do is take the limit. So what is that limit going to look like? So if a was approximately equal to what we have here, all I need to do now is take the limit as n goes to infinity, as we chop this thing up into an infinite number of pieces. So there's the limit as n goes to infinity of, again, I equals 1 up to n, f of x sub I, delta x, where again our delta x is b minus a over n. So as this n goes to infinity, delta x, so delta x is going to go to, oh come on, this goes to infinity, n goes to infinity, the whole thing, let's write it this way, delta x goes to 0 as n goes to infinity. So that's what's going on here. Okay, so let me do an example, and I'm going to come up with a few little weird formulas we're going to need in this section, and then we'll move on and talk about how we can do actual calculus for this. Let me do an actual example. I want to find the area under f of x equals e to the negative x, so a decaying exponential, and I want to find that area between x equals 0 and x equals 2. And for us, let's just use the left endpoints to make this a little bit easier. Okay, so let's start with that approximate area. The area is approximately the sum from I equals 1 to n of f of x sub I times our delta x, which is b minus a over n. So let's get all of these pieces out. In this example, b is 2 and a is 0. They are the starting and stopping points of my interval. So if I do 2 minus 0, the whole width of my region that I'm interested in is 2, right? From 0 to 2, that's a width of 2. And I'm chopping it up into n pieces. So in this case, delta x is just going to be 2 over n. The total width, which is 2, the distance from 0 up to 2, divided by n. So this piece is going to be 2 over n. The f sub xi are going to be the list of all the left endpoints. So again, this piece is 2 over n, and all those xi's are going to be the following. x1 is going to be 0. It's the left endpoint of the first interval. So if I draw this picture over here, maybe it'll help. Got our decaying exponential doing something like this. Here's the x coordinate, here's the y coordinate. I think I went off the page there a little bit. Let's make sure you guys can see that. There we go. We're going from 0 up to 2. This is the region that we're trying to compute the area of. And so I'm going to chop it up into rectangles. Let me get rid of, in fact, all those shaded lines that I just did. I want to do all these little rectangles. And then I want to let the number of rectangles go to infinity. But I'm using the left endpoints. And so that's going to be this point for the first rectangle, this point for the second rectangle, this point for the third, this point for the fourth, this point for the fifth, and so on. All the way up to the last rectangle. I won't be all the way to 2. I'll be at this point that's 1 delta x to the left of the 2. So x1 is going to be 0. This next point, so that point right there is 0. This next point is going to occur at delta x, right? It's 1 width to the right of 0. So x2 is going to be delta x. That's going to be the next point I check, which is just 2 over n. By the time we get to the third point, x sub 3, well, now I have to go 2 widths over, so 2 delta x's. I'm going to be at 2 delta x's to get to that point, which is going to be 2 times my 2 over n, which is 4 over n, and so on and so forth. So if we think about it, these are all the left endpoints. When I eventually get up to, all the way up to the last endpoint, x sub n, for that last rectangle, it's going to be this point right here. This is going to be my x sub n. Right here was this one right here was x sub 1. It started at 0. The left endpoints get me all the way up to this point just to the left of, I'm trying to find a way for you guys. Let me get the mouse out. This point right here is the one. So here's all the left endpoints. Left endpoint of the first rectangle, left endpoint of the second rectangle, left endpoint of the third rectangle, and so on. This is the left endpoint right here of the last rectangle. So I want to figure out what this xn is. Well, I know that it's all the way up to basically, oops, let's get my color correct. It's equal to 2 minus a delta x minus 2 over n. Another way to think about it is, or we've repeated this n times, so we were at 0 the first time, 1 delta x on the second time, 2 delta x's on the third time. I'm going to be n minus 1 delta x's for this last one. Right? So again, the first one I was 0 delta x's, the second one I was 1 delta x, the third I was 2 delta x. How many delta x's is always 1 less than whatever the subscript I is here. So when I is 1, we're at 0 delta x's. When it's 2, we are at 1 delta x. When it's 3, we are at 2 delta x's, and so on. So when it's n, I'm going to be at n minus 1 delta x's. And another way to write that would be, again, n minus 1 times n minus 1 times 2 over n. That would be another way to write that one. So whichever way you want to write it, these two things are mathematically equivalent. You could see that if you just distribute through, but that's what we're trying to get to. So if we start adding up pieces, if we add things up, we will get something that looks like the following. The first point, I need to find the height at x1, and x1 is 0, so I need to find f of 0. But f is that negative exponential, so it's going to be e to the negative 0. Right? I'm just plugging in, it's e to the negative x, and I'm looking at x equals 0 right now, times its delta x, which is 2 over n. The next one is going to be, I'm going to do e to the negative x2, but x2 is 2 over n, so e to the negative 2 over n times its delta x, which was also 2 over n, plus now I will need to evaluate it at the third point, which is 2 delta x's in. That was 4 over n, so this is going to be e to the negative 4 over n times its 2 over n. So these are all the heights. Let me do it in color, actually. I think that would make more sense. Oops, 2 over n. So all the red ones, these are all the heights. And the blue ones, which are all the delta x's, the blue one is the width. And we're just summing them all up. So these are the first 3 little rectangles. We'll continue this on indefinitely, all the way up to the last point, which will be at x sub n, which is this thing. So it's going to be e to the negative, this weird number, n minus 1 over 2n. So however we want to write it is fine. N minus 1 times 2 over n times the 2 over n. So again, there's the height, there's the width. Okay, so this is our big ugly formula with all of these n's. Luckily, this width, 2 over n, 2 over n, 2 over n, 2 over n, appears in every single term, and we can actually factor that one out. So again, this is an approximate area. Undo that. Approximate area. That approximate area, factoring out that 2 over n from everything is going to be, I'll have e to the 0 plus e to the negative 2 over n plus e to the negative 4 over n plus dot 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 plus e to the negative n minus 1 times 2 over n. I've just rewritten this line with the 2 over n's all factored out. So this is our approximate area. That means the exact area comes if we take the limit. So I just need to take the limit as n goes to infinity of 2 over n times this mess. E to the 0 plus e to the negative 2 over n plus e to the negative 4 over n plus dot 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 e to the negative n minus 1 times 2 over n. So there's that limit. Again, this is sort of our long notation. I want to use that summation notation to see if I can figure out the pattern that symbolizes what these terms look like. So rewriting this yet again, we've got the limit as n goes to infinity. I've got the 2 over n. And now this other piece is our big sum. So that's what I want to represent with this sum. It's the sum from I equals 1 to n, and it's e to some power. They're all base e's raised to some power. The first time when I equals 1, I want it to spit out a power of 0. So I need to come up with an expression here. It's going to look like this, essentially. And it's going to give me the power that I'm looking for. So let me plug this in and we'll just check and see that this works. It will. So it's going to be negative. Let me do the 2 out in front. I minus 1 over n. So there's the power. All I've done is take this right here, so this piece over here, and replace that here, but notice this had an n, this has an I, and we can just check and make sure that this is going to work. So let me see if this generates the list that we were going for. So let's let I be equal to 1 the first time through. When I is 1, this number right here is a 1, and I'll get 1 minus 1, which is 0, and I'm multiplying that by negative 2 and then dividing by n. So as long as this is 0, the whole thing is going to be 0. And I'll get the power that I wanted when I was equal to 1. When I plug in I equals 2, I'm hoping to get this power. So when I equals 2, I'll plug in a 2 here. 2 minus 1 is 1. That 1 times negative 2 over n gives me negative 2 over n. And there is my power, negative 2 over n. When I plug in I equals 3, I want to get this one. So when I equals 3, this thing will spit out a 2, and I'll have 2 times my negative 2 over n, which will give me the negative 4 over n that I'm going for. And at the very end, when I is all the way equal to n, so when I equals n, I will get negative 2 times n minus 1 over n. Negative 2 times n minus 1 over n. I get the same thing back. I've just kind of rewritten the way the terms are arranged there. So, this is as good as our answer gets. Without a computer. We want to be able to plug into a computer and have the computer actually spit out a value for this big mess. But this is kind of the approach that we will take to these things. There's some formulas. We'll worry about them down the line later. Maybe we can do some of these examples next time where we actually find some expressions and we can find what some of these weird things actually sum to without a computer. So we'll take a look at that and see how that goes. But for now, I'm just going to leave it like this. We'll do an example down the line, maybe in the next section. One thing that I just want to point out real quickly before we move on is that we've basically said that area under the curve is equal to the idea of an integral. I haven't even introduced the idea of an integral, but I've basically already said this in words. It's true, but it's going to be a little bit more nuanced than that. So I want to give you some warning. Oftentimes in Calc 2, I'll ask my students when they come in, okay, give me the geometric interpretation of an integral. And they all say, oh, it's the area under a curve. Area under a curve is one interpretation of the integral. What's important about an integral is that it's just going to be the sum of a bunch of stuff. We're adding a bunch of stuff up. These things that we're adding up could be a bunch of little bitty tiny areas, in which case we'll get a big area. It could be a bunch of little just lengths, and we'll get a big long length. It could be a bunch of little pieces of mass, and we will get one big large mass. The point is we're adding up a bunch of tiny things. Whatever those tiny things happen to represent, you add up a bunch of tiny pieces of apple, and you get one big piece of apple, right? The units of the small pieces need to match the units of whatever the big sum of all of those little pieces is. So I just want to emphasize this now, and I'll reinforce this even more when we get to the next section in section 5.2. For now, this is as good as it gets without a computer. I've just told you area under the curve is equal to the integral, but this is only one interpretation. And Calculus 2 is going to be a lot easier if you understand that there are other possible interpretations, that at the end of the day an integral is really just a sum. It's not an area, it's a sum. So keep that in mind, and we'll talk more about it in some future videos.